Second day, we're talking about Newton's laws. Let's finish up what we discussed the other day. Okay, Newton's first law review. So I told you, I gave you a definition for Newton's first law. It's objects want to stay traveling at a constant velocity in length while acted on by no forces or balanced forces. This next way I'm going to do it is how I usually picture it in my head. The definition broke down into several pieces. For starters, if you were to look at an object just moving around, how do you know it's following first law? Constant velocity. Okay. You look at an object, most objects around the room are at a constant velocity. What is that constant velocity? Zero. Correct. And right alongside constant velocity, your just basic understanding of kinematics means, of course, acceleration is zero. There's no acceleration. Okay? And along with this comes balanced or no forces. I think I did this demonstration on Friday. I'll probably say it again a handful of times more. Where are you going to have to go for no forces? Space. Which means since we are regularly not in space, which of these two scenarios are we going to be dealing with on a day-to-day basis? Balanced forces. And you see this understood in your force diagrams. For example, right now, as Spainhour is standing here, he has a constant velocity of 0. What's his force diagram? Gravity down and normal up, and those two are balance, equal, opposites, yes, a lot of those things. Okay, let's say, for example, again, this is the demonstration of the day, car traveling down the road at cruise control. At cruise control, we can see all of the particular forces are balanced, okay? And then, of course, no forces. With no forces, Sally floating through space is going to go at a constant velocity forever. Now, Newton's first law of motion is known as, I get a little bit dark with my humor sometimes, I'm sorry, if that bothers you, you just let me know. I'm not going to change, I just want to know. Anyway, the interesting thing about Newton's first law is it's known as Newton's first law of inertia colloquially. Like that's how it's usually said. Newton's first law of inertia. You can say it like that, you don't have to. You say Newton's first law. But the weird thing about calling it that, and the weird thing about talking about inertia, is you actually don't see inertia referenced, or actually like at all, in first law. Meaning, if you are in space and a tennis ball is coming at you at 2 meters a second, and next to that, a bowling ball is coming at you at 2 meters a second, will there be any difference in their motion whatsoever? No, absolutely not. When is there going to be a difference in their motion?
There's gravity.
Or not necessarily. No, in space, we can stick in space. Say that a little bit. You're 100% right. But, all right. Are you using her? It's fine. I can use her hypothetically. They know what she looks like. It's fine. We're good.
Okay. Do you want to tell her bye?
Bye, Sam.
We're going to go here.
Have a good time. All right, off we go. I tell my kids the same way. Anyway, yeah, so it doesn't happen until if Sally or the tennis ball actually change their velocity. Okay? Like if you try to catch the tennis ball or catch Sally, you're going to feel the difference of inertia. For example, we talked about this with Sally ball the other day. What does hitting Sally do? Changes her
Acceleration.
well, actually, let's say accelerate or changes velocity. But yes, absolutely. We don't change acceleration here, blah, blah, blah. It's not important. But that's when you really felt the difference between Sally and the tennis ball. When I asked you, would the tennis ball be easier or harder to play? All of you said one way or the other, easier or harder, but you said it for the same reason, because the tennis ball is going to be easier to change. Easier to get going, right, which is an acceleration. Easier to stop, which is an acceleration. And easier to change direction, also an acceleration. But if the tennis ball and the bowling ball are just going through space, I was going to say here on Earth, it would be a little bit different here on Earth, but if they're just going through space at you, are you going to be able to tell the difference? So again, it's a little bit weird that this one's called Newton's first law of inertia when you don't actually see inertia yet at all. We will get to that today. All right. Bell ringer. I have 2 bell ringers. I want to do this one. Do I want to do the second one? Yes, we will. But let's do this one at a time. All right, so take about 2-3 minutes. You can write this down. You don't have, actually, I do want you to draw, but the main thing here is work in your group. Discuss in your group what the answer is, what it should be. So you're driving along in a car, Bumblebee, or just a car. If you don't know, my reference is to Transformers. An Decepticon jumps in front of the car, and the driver's forced to slam on the brakes. Without a seatbelt, you're going to fly forward. Explain why. Then draw the force diagram right after you being hit, both with and without a seatbelt. So two separate force diagrams for both of those two scenarios. So obviously you have to draw them, but if you just want to discuss the first one with everybody else, it'll be fine. If it helps to put a number to it, we'll say that Bumblebee's traveling 60 miles an hour down the road. 60 miles an hour, then slams on the brakes. Those of you on the video, I'll try to put on timestamps so you can skip ahead to the discussion. My wife's still on music again. I want to steal it back so you can see what she's listening to. I'll still steal it right now. This is what she and my kids are listening to. It's the theme song to the Goofy movie. All right, let's not take forever on this. Because some of these things, please understand, especially early in a chapter, I know I say it 1,000 times, but it's so ridiculously important for you to kind of get over the right answer. You're not going to get the right answer immediately because your brain is not kind of programmed yet that way. So one of the most important things when we're in these cases, make a wrong answer. Like, I don't know, I don't care, so put something. I don't care if it's wrong. The key thing there is make those adjustments. All right, so why does the person fly forward?
There's no force holding it back.
That's okay. So yes and no. Yes, you're 100% right. There's a word you should probably have in there. If the person is traveling right now down the road at 60 miles an hour, okay, this feels like how fast are they going? 60 miles an hour. Doesn't matter that the car is also going 60 miles an hour. They are going 60 miles an hour, right? So why do they continue forward when the brakes are slammed? They're still going 60 miles an hour. 100%. And on top of that, keep in mind when I say the brakes, the force diagram of the car is not the force diagram of the person. They are not the same force diagram at all. Just because I slam on the brakes of the car, does that have any effect on the person whatsoever? No. So, the key word that I would be looking for there, and previous year's physics classes will tell you that if you don't know the answer, this is usually the answer, and a lot of times early on it is, but you should probably explore better, is inertia. So if you ever don't know an answer, by the way, in here, and I get it, it looks like I'm waiting, just somebody throw out inertia. Just like, inertia? Yeah, okay, that's probably it. So, the person's sitting in the vehicle. Now, one thing that's hard to kind of grasp, and I have them obviously not leaning on the back seat right now for the sake of kind of just understanding this a little bit better and not adding some complexity. But here they are. They're sitting on their seat of the chair, okay? And this is let's say right before they get hit. Okay, right before they get hit, what's the force diagram on the person? Force gravity. Force of chair on person, which way? Okay. And this is one of those where, like, could I use force normal? Is a car a solid and movable object? No and yes. I'd be fine either way. Okay, if you said force normal, who cares? But yeah, that's it. That's literally it. It's weird to have that. like you're looking at that and you go like, wait, but what force is pushing it forward? But again, do we need a force pushing forward? No. That being said, it's still going to be hard to kind of get over it for yourself. So you don't have a seatbelt. What's the force diagram? That one. So what happens? Well, technically, nothing happened to you at all. You technically don't fly forward. You just continue flying while the car has a force diagram like this. So what's the car do? The car stops. The problem is, of course, you fly forward because you don't stop. So what changes when you put what changes when you put a seatbelt on? Yeah, you have a force of seatbelt on person here in this particular case, which of course is what provides your necessary force backwards in order to do that. By the way, a couple things. If so, we're a little bit more realistic. You can be like, yeah, but Spainhour, at slow speeds, I'm completely fine to sit there. Yes, your butt actually does have a good amount of surface friction with the chair underneath you in that case. So you can get a little bit of force friction as long as your butt stays connected to the chair. But if you're going at 60 miles an hour, your butt's not staying connected to that chair very long, which means the moment you're not touching that chair anymore, that goes away. Here's your force diagram. Well, technically, that's your force diagram until you hit the window. And you hit the window, and there'll be a little bit of force backwards, slowing you down a little bit. But of course, that window's going to break. And so that's going to go back away. Technically, you won't be touching the chair anymore, so it's going to be this. And then if we zoom in on this particular one, I don't know where this became a safety, like PSA for seatbelts, but here we go. Now you're out of the air because of this, and your force diagram looks like this. And since you only have force gravity on it, if we ignore force friction, you are now in projectile motion. So you are a projectile launched at 60 miles an hour, roughly horizontally. And we can figure out where you land, but it doesn't matter because you're not going to be happy when you get there anyway. All right, so next force diagram, or next bell ring. Here we go. Oops, went wrong. Force diagram for each of the following when I throw the marker in the air. I'm pushing it up, and so it's going up. So here we are. I'm just going to toss it in the air. We've used this example 2 or 3 times. For those of you on the video not watching me, I am literally just throwing a pen in the air. You can use your imagination. They really don't need me to do this. But I want you to draw a force diagram for several times. 1, while I'm pushing it up and it's going up. 2, it's in the air but still going up. 3, it's in the air coming down. And 4, while I catch it after it comes back down. We're going to go ahead and assume that this is moving slow enough that air friction is negligible. It is there, you're 100% right. We're going to ignore it right now because this object is moving slow enough. So if you would draw the force diagram for those 4 times, I'll give you like 2 minutes and then away we go.
We're drawing it for the pen, right?
For the pen, yes, correct. All right, so I'm going to draw 2 force diagrams. You tell me which one is right and why. So in both force diagrams, I'm going to draw force of gravity down exactly the same. In this one, I'm going to draw force of hand on pen. In this one, I'm going to draw force of hand on pen. Which one is the correct one and why? The second one is correct. How do you know the second one is correct? That's not quite right. That's not quite right either. What did you say?
You're throwing it up with the greater force than gravity.
Why? How do you know?
Because it's going up.
Let's say this differently, okay? I'm going to tell you that this pen, I'm going to ask you a different question based on what we said earlier. This pen, when it's in contact with my hand, is it following Newton's first law? Why or why not? Let me start easier. I'm walking across the front of the road. Am I following Newton's first law? Why or why not? Yes, I am following Newton's first law. Why? First thing we started with today. Sorry, someone said it, I thought. Constant velocity, correct. Constant velocity. Constant velocity can, of course, mean the object is stopped. It can also mean the object is moving, like we have seen with me walking across the front of the room, with the car traveling at a constant velocity. So, I will go back to this. As the marker is being pushed up in the air, as it was touching my hand, is it following first law or not? No, because it's accelerating, and it's accelerating upwards, which is what tells us that this should be bigger than that one right there, right? For example, if I were to take the pen and lift it like this, for those of you in the video, I'm lifting it at a constant velocity, then that is my force diagram. They are equal and opposite of each other in that particular case. So, yeah, the second one right there. Number 2 should be really easy. It's just force of gravity, which makes sense because we talked all about this in 1D kinematics. What's the acceleration while it's up in the air? 9.8 down, yep, 9.8 meters per second squared, which is gravity, which is because of this right here. Also, the third one over here is exactly the same. Notice it doesn't change at all. Okay, the key thing that I wanted to show you here, a couple deals up. Here's number 1. I wanted to talk about Newton's, well, not first law so far with this guy right here. And 2, the other thing I wanted to show you with these 2 examples is we don't care. We do not care which way an object is moving. Velocity is not seen on force diagrams. What is seen on force diagrams is the direction of acceleration. Here, acceleration is up, so force hand on pen wins. These 2, this next 2, force acceleration is down at 9, acceleration is 9.8 meters per second squared, but it stays down the entire time. What is this guy's force diagram? The exact same as what it started a second ago. Why? Why is it exact same when I catch it?
The force of the hand pushing it up is greater because it's changing the velocity from the going down to 0.
I'm going to say that a little bit more succinctly. Everything you said was correct there. It's accelerating upwards. The velocity is down, right? I'm slowing it down, so acceleration is up, and therefore this guy should win. How we do it? This leads us perfectly into second law, because first law was when it's at a constant velocity. All 4 of these force diagrams in this demonstration are actually not a constant velocity, which means they should probably go to a different law. So let's start talking about that now. If first law, let's go back to first law real quick. Blah, 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 we did that. If first law is constant velocity, 0 acceleration, and balance or no forces, I'm going to go ahead and guess it's not going to take very much effort for you guys to figure out second law very much. So we're going to take it in a different direction. But I bet you could tell me second law right now. If this is first law, let's just run through it. Guess what second law is? Changing. Sure. Change in velocity. Okay. Acceleration? Not 0, right? Okay. And forces? Unbalanced. Correct. You nailed it. That is second law in a nutshell. So why should we spend so much time on it, Spainhour? Well, I've said to you a second ago, I forgot I hadn't said to you. Yep. I said to you a minute ago that it's weird that first law doesn't address inertia because you don't really see inertia. What measures inertia, by the way? What is the measurement of inertia? Like does a bowling ball or a tennis ball have more inertia? Bowling ball. How come?
It's measured by mass.
It's measured by mass. Correct. It has more stuff in it. So, got a tennis ball. Obviously, I don't have Franklin here will be the you'll be the placeholder for the tennis ball. All right. Anyway, so Franklin. Remember today, Franklin is a bowling ball. Okay, he's not, but in your head, he'll be a variable object representing a bowling ball. So he's a bowling ball. Okay. So obviously, if this is thrown at you, you're going to be able to stop it pretty easily because it has a certain number of atoms. So if Franklin here has 10 times the amount of atoms, okay, then you would expect to be 10 times harder to stop, meaning it has 10 times the inertia, 10 times that. So let's address something that has always been weird. Why the heck does everything accelerate at 9.8 meters per second squared? This has been a weird thing that people kind of just pass because I teach you that it's not the case, and so people very quickly go, oh, okay, it's just not the case. But if you have moved past the fact that it's weird, I have a problem with that. Like, we did this whole demonstration, which one of these hits first, and everybody kind of natural has an inclination towards the book, and you're 100% right. It is the book, but it's because of air. But like, if there is no air, or we don't consider air, of course you know the answer to this. Okay, which one accelerates more? It's the same. Isn't that weird? Isn't that ridiculously weird? I mean, that's pushed more to the ground, is it not? Is it not pushed more to the ground? Like, okay, let me give you a demonstration. Okay, let's say you got 3 siblings. Okay, and no, actually for this example, we only need 1 sibling for this example. Never mind. So you have 1 sibling. Okay, they're younger because it matters, or older if you're more confident than them. All right, and they walk down the hallway, and you decide to perform a scientific experiment on them as you're going. Okay, so like Monday they come by and you shove them a little. Okay, and then like Tuesday you come by and you shove them more. All right, and then whatever Wednesday, whatever the next day is, you shove them really, really hard. Do they accelerate differently each time? Yeah. Well, let's demonstrate. I need a volunteer. No, you don't get to point. Come on up. Come on up. You do not volunteer someone else in my class without being volunteered. Volunteering someone else in my class is the volunteer. Now, I think you're going to be very happy that you got accidentally volunteered here. Okay, so I would like you to shove me a little bit. Okay. Did I accelerate?
Yes.
Yeah, I wasn't moving. I definitely was moving fast. I had to stop myself. All right, I need you to shove me a medium bit. Okay. Did I accelerate a little bit more?
Yeah.
Okay. I kind of played it up a little bit there, but I need you to shove me a lot of it. All right, so definitely, all right, you can have a seat. That's all we needed to do. All right, so in case you couldn't picture this in your head, I needed something to actually, it was 100% necessary to the example. Point being, if you push harder, will you expect it to accelerate more? Yeah, of course you would. So isn't it weird that everything accelerates the same? I mean, think about it. Hold these up. Is one of them definitely pushed harder to the ground? Yes, without a question. Hold these. This is pushed harder. When you push someone more, you expect them to accelerate more. So why the heck does everything accelerate at 9.8 meters per second squared? Mass has 2 properties, though. What are the 2 properties of mass? Gravity. The first one, I'm going to get you the second one in just a second. The first one we just dealt with, this is pushed harder. This book is pushed harder because it has more gravity. It has more pull. It has more pull between it and the earth than this and the earth because it has more mass. So there's more of a pull downward. There's more of a push. Yes? What is the second property of mass? Inertia. Take your pen real quick. And whose hair is this? I mean, at home, my wife's hair gets everywhere, but like that can't be here. We'll leave it. Is it very easy to change the velocity of your pen? It's easy to accelerate the velocity of your pen. How come?
Doesn't have much mass.
There's not much mass. Very easy to change its velocity. Pick up a textbook. Try to do the same thing. Just as fast. Is it going to happen? No. How come? There's more mass because there's more inertia. There's more inertia, yes. So like if I were to play catch with the tennis ball, we can feel inertia, right? Because it's easy to get going. It's easy to stop. When Sean and I played catch with the tennis ball, It was easy to get going. It was easy to stop. When we played catch with the bowling ball, it was hard to get going. It was hard to stop. I don't know the exact numbers, but I'm just going to make up something. Let's say this has 10 times the atoms that this does. That means it has 10 times the mass, which means it has 10 times the force of gravity on this one. So it has 10 times the pull to the ground. My arm on this side has to pull 10 times harder on this guy than it does on that one. Make sense? I mean, that's just easy stuff. Go to the gym, somebody puts a plate on, and then one over, somebody puts 10 plates on, you go, that one's going to be 10 times harder to push than this one over here. I mean, that's like super basic intelligence. So why do they accelerate differently? Because this one has 10 times the atoms that this one. So yes, it's pulled 10 times harder, but it's 10 times harder to get going. Let's go back to my sibling example, and now I will borrow the 3 different siblings. We have a small sibling, a medium sibling, and a large sibling. And they're all going to dinner on the same night, I guess Thursday, because we're just going progressively here, right? So the big one comes by and you shove them, and apparently they just keep walking for the sake of this example. The medium one comes by and you shove them the same. You shove them the exact same amount as the first. And the small one comes by and you shove them the same. Does it affect all of them the same? No. Who gets affected the most? Because less mass, they have the smallest amount of inertia. Everything accelerates on Earth the same because of gravity, because mass affects gravity, and inertia the same. This one is pulled 10 times harder, but it's 10 times harder to get going. In my example with the siblings, as they were passing by just a second ago, I said you pushed them the same. But if the big sibling is 3 times bigger than the small sibling, and you push the small sibling, but then you push the big sibling 3 times harder, then the effect would be the same. Because both the force and the inertia both tripled. How are we doing here? Let's give one more kind of help out thing. Imagine, for example, Newton's second law. We have a bowling ball and a tennis ball, or apparently Franklin. Thanks, buddy. Barrington. All right, anyway. We drop both of them. So this is the demonstration. The tennis ball has a small amount of force. The bowling ball has a larger amount of force. But the tennis ball has a small amount of mass, or inertia. The bowling ball has a larger amount of mass. But these numbers are proportional because they're both affected by mass, right? So if I put numbers to it, this is the force on a tennis ball and its mass. And here's a force on a bowling ball and its mass. You'll notice both the force and the mass got bigger. And if you divide both of these two sets of numbers, any idea what number you get? 9.8 meters per second squared. So everything accelerates the same, because if you get bigger mass, you definitely get more push, but you're also just as hard to get moving. Now what we just did in that conversation, which you might not have noticed, is we actually spelled out Newton's second law. And it's this. If you push something harder, what do you expect to happen to its acceleration? You expect it to go up. But if you push two different objects with one having a larger mass, the one with a larger mass should accelerate less. So force is proportional to acceleration, meaning double that, but mass is inversely proportional to acceleration, double that, cut that in half. See that? So if I double both of them, or multiply both of them by 10, what effect does that have on acceleration? None. Absolutely none whatsoever. It stays the exact same size. Now what you might notice in this example, hopefully, is this only works for gravity. It only works for gravity because gravity is the only force that also goes up with mass. It doesn't work with electromagnetism. When I was shoving my siblings, or you were shoving your siblings, that's electromagnetism, which is not affected by mass. All right, so Newton's second law. We already said it. How do you know it's second law? It's changing velocity. There's its equation. This weird little symbol right here, which you may or may not be used to, is very important. That is a sigma. That is the capital sigma. If your brothers or sisters or friends or whatever have joined a fraternity and they have sigma, that letter would be in there. And unbalanced forces. So if I walk across the front of the room, okay, I stand here, I walk across the front of the room, and then I stand here. When were the examples of first law? When was I following first law in that? And it's not just once, it was several times. When I was standing? Correct. When I was standing over there, when I was walking at the constant velocity that most people walk at, and then when I was standing here. When was I following second? Yep. When I sped up, when I stopped over here, both of those are examples of second. So if you run into something, or if you punch something, or if you push something unbalancedly, you're gonna cause it. Like, so when you get going today, right now all of you are at 0, all of you are currently following first. When you get going, you'll follow second for a brief moment, and then if you're traveling down the hallway, you're more than likely gonna be following first. And you'll follow second if you stop, or slow down, or speed up, or change direction, but we'll get to that in chapter 7. Or like if you decided you really believed in the Harry Potter movies, and you were like, you know what, platform 9 3/4 is a thing, I just gotta commit. Do it! It didn't work. It did work, but while he was making contact with the wall, second law. Also, I'm going to go back real quick because I totally forgot about this. So this equation is the best way to understand second law. However, if you've heard anything about physics ever, you might have heard force equals mass times acceleration. This is the most common way to write Newton's second law right over here. Sum of forces is equal to mass times acceleration. They still do the same thing, but the main thing to get out of Newton's second law is how these two things affect acceleration, which is why we regularly have it like this. But that's still, I mean, this is just algebraic, the simplest algebra ever to get over here, but that's usually how we see it. So if you run into a wall, this is your force diagram, and you can see in a force diagram very quickly when it follows first or follows second. As a matter of fact, a good amount of the force diagrams that you guys have been doing, I gave you that hint, you should be able to very quickly go back to all of them and go first, second, first. And you can find them in two ways. Either one, it straight up says it's constant velocity or changing velocity, or two, just look at the picture, right? Looking at the picture, if the arrows are balanced and you've done it correctly, then it falls first. And if they're unbalanced, then it falls second. Okay, a couple quick things here. We're going to knock out third here pretty quick here at the end, but we do need to address this. Number one, at the very top there, you're going to hear a lot of synonymous words. So I want to make sure to kind of cover those right now. This is known as sum of forces, or force net, or resultant force, or total force. All of those words mean the exact same thing. I don't think I have it up there, but the other one that's usually with that is sum of forces. That's actually mathematically, you know how we know that the triangle delta stands for the change in, to the point that we don't even see delta anymore. Same sort of thing here. What this word means in terms of words is sum of. The sum of forces. All right, several of these units you really already know. What are the units for mass? Ooh, close. Kilograms. And the only difference is you're 100% right that it is grams. But, okay, this right here is a single kilogram, right? A gram is 1,000th of that, which is so ridiculously tiny that 100% they use it over in chemistry because they want to use small things. Over here, I would be, or you would be, somewhere on the range of something like somewhere between 50 to 80,000 grams. Why do we use kilograms? I don't want to write a bunch of extra zeros because I'm going to forget to write a zero and screw up, so let's go ahead and use kilograms. All right, acceleration should be easy. What are its units? Now, before you kind of jump ahead, and maybe you know the answer to this already, we should be always able to do that unit analysis stuff from chapter 1, which is if we don't know what something is, we should be able to combine this side to tell us what that side is. So what are the units for force based on that? So what that means mathematically is this. We define force as taking 1 kilogram the amount of push necessary to accelerate this at 1 meter per second squared is this force. And we give that a name because we don't want to put a bunch of extra units in a thing. Scientists are like, hey, I don't want to write a kilogram meter per second squared every single time, so somebody pick a fancy name. Well, it's his laws, so let's call him a Newton. So what is a Newton? A Newton is a kilogram meter per second squared by definition. And the most important thing that you need to get out of that is this. That means if you're using Newtons, which you're going to be, you should regularly, the units of these others have to be in kilograms and have to be in meters per second squared. You can't be in feet, you can't be in hours, you can't be in minutes, you can't be in grams, you must be in kilograms and meters per second squared. Also, because I don't think it's up here yet, let's get this down because you're not used to Newtons yet. The equivalency, I've told you regularly that mass is not weight. Okay, because here's the best way to say it: mass is inertia, well, and force of gravity. Force is the oomph. Force, and therefore in kilograms, force is the push, and is measured in newtons. Pounds, which you are most used to, is not this one. Pounds is another measurement of force. So they're equated to pounds. To help you out with that, this conversion you're going to use a ton in this chapter. 4.45 newtons is equal to 1 pound. So that means a 100-pound person, he's light, congratulations. A 100-pound person is 445 newtons. These numbers sound like larger than when I start to say like a 700 newton person, you go, oh, good night. Remember, 700 newtons is not 700 pounds. Okay, 700 newtons would be a 70 kilogram person. This is about 150 pounds-ish. Okay, so you're gonna have to start to get a little bit used to what a newton is, and the best way to do that is to compare it to stuff that you already know. For example, if you took your weight right now, plugged it into a calculator or something like that, multiplied by 4.45, that's how many newtons you would be. All right, almost done here. Now, why? Here's first and second law again in a nutshell. Okay, we've already done this, but constant velocity, zero acceleration, balanced, or no forces. And there's second law when it is accelerating. Now, if you think about that carefully, you go, Spainhour, there's nothing left. You've discussed when objects are changing velocity or when they're constant velocity. There is no other option other than those two. So why is there a third law? Well, the reason why there is a third law is this. The first and second law, which by the way is what we primarily focus on in this chapter, which is why I've spent a bulk of the time on them, are covering just, where's it at? Oh, by the way, oh yeah, I meant to say this over here. Okay, so you know how I said sum of force is equal to mass times acceleration? Well, what's it called? What would acceleration be if it's following first law? Zero. So that would cancel out the mass and acceleration, which would mean in first law, you could say balanced forces means this. Balanced forces is sum of forces is equal to zero. We'll talk a lot more about this math tomorrow so you can see it a little bit from another perspective. But both of these laws cover a single object. As we talked about in force diagrams, if I get mad at this chair and I push the chair, I fling the chair across the front of the room. If we're doing a force diagram on me, if you're doing a force diagram of me in this case, you would not see the force on this chair going that way, right? Weirdly, actually, if Spainhour throws a chair that way, there's a force of Spainhour on chair. There's actually, because my electrons are hitting the chair pushing it that way, what are its electrons doing? Pushing me back the other way. So actually there'd be a force back the other way, which brings me to Newton's third law. Try this. Take a finger, touch the other finger. Okay, so you got two fingers pressing like this. This is a dumb example, but it's really important to kind of come to terms with. Is it possible for one finger to touch the other and not vice versa? Is it possible at all for one finger to touch this one and not have the other touch back? Now think about that with anything. If I hit the table, is it possible for me to hit the table and the table to not hit me back? No, when you really think about it, it's electrons. right? It's electrons of my hand hitting the electrons of the table. So if my electrons push it that way, then its electrons push me the other way. Most people answer this question correctly innately. They struggle then with the next one. A semi is traveling down the road and hits a bug at 60 miles an hour. Discuss quickly in your group. Which one feels more force? The truck or the bug? Discuss. It helps. I did warn you that most people get it wrong. Discuss. Use words, not telepathy. So you gotta, if you don't know, you're sitting there, I have no idea where to start with this. Give other people what the gut feel is, or I'm pretty sure this is the wrong answer, but also, just, what do you think? What do you think? So there's a truck, there's a bug, okay? The truck hits the bug, okay? Probably not gonna make that big of a sound, okay? Hits the bug, which one feels more force? The bug or the truck? Discuss. All right, let's set it up like this, because obviously by telling you that most people get it wrong, you're probably leaning away from your initial answer. What was your initial, obvious answer? The bug. Obviously it's the bug. But zoom in crazy far on that situation. Why does the bug feel force at all? Like if you zoomed in crazy, what's causing that force? Electrons. Electrons in the truck hitting the electrons in the bug. So let's say there's this is a bigger number than this. Let's say there's 5 electrons in the truck hitting 5 electrons of the bug. Should one feel more force than the other? No. These 5 are going to hit these 5 the same way. Now what you're looking at potentially there is that both of them get a different effect. Agreed. But they get the same push in the same way, okay? I've got a 2-year-old. I've got a 6-month-old. If I shove them the same, they're not going to get the same effect. Hypothetically, I'm not going to do it until they get older. Okay? When they get older, I will absolutely use them as. I push the 2-year-old around all the time, especially if we're on a trampoline. Just see what happens. It's scientific experimentation. It's not. Why do you have kids after all? All right. Anyway, so you shove one, you shove the other. It's not the same. If I shoved a bug and I shoved the truck, would it be the same? How come? Come on, guys. What did I tell you earlier? If you don't know the answer to the question, it's inertia. Yeah. All right. Or it's this. I'm going to make up some numbers here, but it's Newton's second law because both of them are going to accelerate. If the truck gets 100 newtons of force, by the way, a truck being 10,000 or so. I'm sorry, actually, let's not go 100. That's going to be ridiculous. Let's go 10. 10 newtons of force. The truck has a mass of 1,000 kilograms. Basic algebra here means it accelerates at 0.01 meters per second squared. You're probably going to notice that acceleration in the truck? No. We go over here, and the bug gets the same amount of force, 10 newtons. But the bug's 1 gram, or 0.001 kilograms. So the bug receives an acceleration of 10,000 meters per second squared. To put that in perspective for you real quick, if you would like to accelerate at 10,000 meters per second squared, take your weight and multiply by 1,000. That's how hard we have to hit you to accelerate you at 10,000 meters per second squared. It's a bit. So, do they get the same effect? No, but it's because of inertia, not because of the force. A few more examples and then we're done. So here's Newton's third law. For every force, there's an equal and opposite force in the opposite direction. If Spanauer hits a wall, the wall hits Spanauer. If Spanauer pushes the floor pushes Spanauer back. Okay? If Gabe slaps Spanauer in the face, Spanauer's face slaps Gabe in the hand. Here's the mathematical way to write it so that you don't have to write this giant thing every single time. These forces, by the way, reaction forces. The force of 1 on 2 is equal to the negative force of 2 on 1. But I want you to point this out. Notice this carefully. These forces go on different objects. This first force goes on 2. The second force goes on 1. You will never see this is known as a third order pair. You will never see a third order pair on the same force diagram ever. It does not happen. They have to go on separate objects. If Spanauer punches the wall, then the force of Spanauer on wall goes on the wall. Honestly, for me, I don't care about that. What I care about is that even though Spanauer hit the wall hits Spanauer back. The opposite way potentially breaks his hand. Here's a quick question for you that I think is interesting. Let's get this piece of paper back out here. If I punch the wall, there's a good chance I break my hand. 100%. If I punch this piece of paper out of the air, there's a good chance I break my hand. Both put an equal force back. Why will I not break my hand when hitting the piece of paper versus I'm not going to demonstrate the wall? Yep, that one's easier to move. So that one doesn't take nearly as much force to accelerate it. But that one over there takes a huge amount of force to accelerate it and therefore puts a huge amount of force back on my hand. There we go. Forces must appear on separate force diagrams. I said that already, but I'm going to move on to my last examples. How about this? Here's a weird one. We've said force of gravity. What are the two objects on this guy right here? What are the two objects in question for force of gravity? Or let's say your weight. Okay, your weight pulling you down right now. What are the two objects for force of gravity? The Earth and you. Now, what I have tried to avoid talking about because it's messy until this point is that so the Earth is pulling you down at your weight. According to this, you are pulling the Earth which way? Up. How much? The exact same amount. If you weigh 150 pounds, because the Earth is pulling you down, guess how much you're pulling the Earth? 150 pounds. But who's going to get affected more by that? You, because you have a mass of something like 50 to 70 kilograms. It has a mass of 5.98 times 10 to the 24th kilograms. So is it technically going to accelerate when you fall down? Technically it will. But like if you round it, we'll just go ahead and call that 0. Right? So does it? Yes. Punching someone. We talked about Gabe slapping me. Okay? He goes to a judge after punching me in the face because of being annoyed, points, or I don't know. Who cares? Punches me in the face. He goes to the judge. Look, listen, judge. I know what you're saying. I punched him in the face. But physics says, hear me out. Physics says that not only did I punch him in the face, but equally he's the fault because his face punched me in the hand. Repeatedly. And technically, if you go to relative motion, we don't have a holding 0. So from the Earth's perspective, this happened, right? But from the physic's perspective, my perspective, here's what happened. Ray slammed his face into my hand multiple times in a row. And my hand hurts. Don't try that, it doesn't work. Last one of my favorite examples is rifle recoil, okay? And feel like guns, whatever, it's just a good example. If you fire a gun this way, you put a force of a gun on the bullet. Newton's third law says if you put a force of a gun on the bullet, then there is an equal force of the bullet back on the gun. So you might not have experience with guns, but you can probably feel this pretty well. Should there be a bigger recoil in a handgun or a rifle? Handgun. Simple reason why. What is it? Yep. Told you, inertia's the answer a lot of the time. Why would it be a terrible idea to design a gun that is the exact same size as the bullet? You fire a gun that way at 300 meters per second. The gun is going to go that way at 300 meters per second. Last thing I have for you is a video. It was really hard to find a video of rifle recoil where someone wasn't cursing. Okay? Feel free to look them up on your own. My favorite one is the woman that's holding the Desert Eagle.
Dad, do you want to go first?
No, you go.
Yo, buckler.
I'm gonna charge you.
It's not that big, I just jumped up.
Yeah, poor kid. Anyway, he doesn't cuss because he's small, but everybody else does when they get older. So there you go, Newton's third law. We'll move on tomorrow.